the main purpose of today is about science. So let's talk a little bit about what motivates battery research, because it's a very difficult topic to give, because when it comes with batteries, everybody has opinions, because you all have batteries in your pocket, right? So I hope to deliver to you a lecture that is targeted at general audience that with no scientific background. But can you raise hand if you're trained as a scientist or engineers? Okay, good. I think that will make my job a little bit easier if you are actually trained engineers or scientists. Okay, so in California, I think we all believe that in the next couple of decades, we have to do deep decarbonization. So I think this is the energy chart for the US. We just reprocessed the data. Actually, in 2017, the picture has not changed much since compared to 2015. Basically, the CO2 source comes from three major parts. 1/3 comes from transportation, right? 1/3 comes from electricity production and transmission for the electricity distribution. And the other things, so actually you see for the transportation session, petroleum occupies most of, no matter what happened in the electric car in the last few years, petroleum still dominates. Okay, and in the sessions for electricity, natural gas is replacing coal little by little. More, I think in 2017, you're going to see more blue, less of the gray color. So in terms of deep decarbonization, it's very clear that we have to work first on the transportation session, and then we work out how we can make our electricity green. So here is a potential ethical issues that I can discuss with everybody. So I think a lot of people regard batteries as renewable. We're not, okay? Battery is just to many people, is a black box. You put electrons in, you plug in, you use it when you need it. So electrons has no colors. We don't care if the electrons are generated by burning coals, or the electricities come from the wind and the solar. So when people are doing a lot of the push for the electric cars for transportation, I think a more holistic way to look at it is to check the grid. How green is your grid? So for instance, in California, close to 25% of our electricity is generated by wind and the solar, right? So that means majority of the electrons are not green color. Anybody from Washington States? Okay, in the Washington States, more than 60% of the electrons for the grid is generated by hydro, very green. So it's a no-brainer in the Seattle area or in Washington State, you drive electric cars. Okay, so this is a potential things I would love to discuss with the audience, because I do think that yes, we made a lot of progress thanks to Elon Musk, a lot of momentum for electric cars, but I think the real crown jewel for the deep decarbonization is actually on electricity. We have to find ways to modernize our grid to make sure we use more renewable and sustainable power sources. Then it makes more sense for us to drive electric cars. Okay? Doesn't mean that we should not drive electric cars now. We just have to know what are the factors that are being considered when you purchase electric cars. Battery research is actually a booming field. I talked about electric cars. This is the Tesla Model 3. So UTC Mall has the models already displayed. I queued for half an hour to sit in the driver's seat last weekend. And this is the BMW i8. All the electric cars, modern electric cars, are built the same way as petroleum cars, sometimes even more attractive. I think they learned from the mistakes in the old days that electric cars all look very weird. I think those cars do not look weird. Right? We also have a very big program in Sustainable Power and Energy Center to work on batteries for wearables. I mean, particularly we have a lot of interest from the medical field that things that you wear that are powered by batteries that can give you signals about your health information, about a lot of, when you exercise, what are the benefits you're getting, those kind of batteries, in fact, does not solve the global climate change issues, but indirectly it contributes, because you could also imagine that this kind of wearable devices could be used for home energy monitoring and many other potential applications. And the last one for the wind and the solar, I can tell you, hopefully today, after today's lecture, I can tell you the scientists don't have an answer. We don't have a clear answer what's going to be the next magical batteries that can actually enable us to store all the wind power and all the solar powers, right? For many reasons I will give later. So as I mentioned, that this is the black box. Most of people regard batteries, it has a positive electrode, a negative electrode. All you need to do is to make sure that when the bulb connects, LED will light up. Okay, let me show you from a material scientist perspective how a battery should look like. Okay, yeah, so that's where I ask some of the trained engineer and scientists. I think I'm going to use a few jargons here. Okay, so the negative electrode, the battery is, it works. It's really a magic that it works. Okay, you actually use graphite. The pencil? Graphite is actually used in the negative electrode. So everybody knows the fancy words of graphene, right? Graphene is a single layer of carbon. Graphite is multi-layers. On the positive electrode side, you also see those sheets, layers. But this time the sheets are more complex because they are made with a transition metal, which like cobalt, nickel, manganese. They are surrounded by 6 oxygen, but they still, if the scientists find the right way to synthesize it, they arrange in this perfect ordered form. It's called a layered oxide. Okay, so basically the lithium ions have very different energy between the two hosts. So you can imagine that, when I go to my in-laws' house, my energy level is very high, very restless. Okay? Okay? When I'm at my own home, energy level very stable. I'm very comfortable at my own house. All right? Just imagine that you're shuffling between the two houses. Okay? The energy levels are different. And that's how the chemical energy of the lithium in the graphite is very unstable. The chemical energy of the lithium in the transition metal oxide, stable. Okay? This difference, the chemical energy difference, is what gives you the energy in your batteries. So basically, when you're charging your batteries, you are plugged in, you supply the electricity to drive all the lithium from a stable situation to the unstable situation where the chemical energy is stored. When you use it, it's actually just a load outside, and then it automatically releases. So why lithium-ion batteries is such a magical thing, why it can cycle a few hundred cycles without failure? Because when you shuffle the ions in between of two, right, the whole structure is mostly unchanged. Okay, so now people ask me, Shirley, actually I don't like my batteries because it always, fail. After I use sometimes it degrades. They said it's going to last my laptop for 4 hours. Now only get 2 hours. Actually, the modern iPhones promise you 8 hours the whole day without charging, right? So what are the failure mechanisms? Actually, when we talk about batteries, I'll draw an analogy of batteries with airplanes. What's the most dangerous time when you sit in an airplane? It's when it's taking off and landing. Why is that so? Because the atmosphere pressure on the ground and on the high altitude is different, right? The materials, the airplane has to go through basically a pressure cycle when it's landing and taking off. Same thing here. When all the lithium is squeezed on one side, the volume of the materials has to expand a little bit to accommodate all the lithium ions. So remember, for batteries, the electron mobility comes from the ions. The ion is matter. Matter is what gives you the energy. Right? So there is a chemical bond breaking in the formation process. So the volume change of these materials, you cannot observe it by eyes. And I will show you, you need the high-end instrument, like what doctor used for patients, NMR, X-ray. Yeah, we have to use X-ray to observe those changes. And typically, each time you cycle the batteries, the battery goes through a few percentage of volume changes reversibly. So you can imagine, after many cycles, the battery material is tired. Just like the airplanes, actually all the airplanes will retire after certain years of service. They cannot keep going because the materials go through a process called a fatigue. There will be defect generated, and then you cannot use it. Okay? And the last thing I want to tell the audience here is that the active materials used in the battery is only 25% of the total weight of your batteries. This is how today modern battery is designed, because you have to have a lot of casing materials. You have to, for lithium-ion battery, you have to have the BMS, the battery management system. Actually, for electric car, for large systems, you actually need the cooling system. You need a thermal management system, right? So from the materials level all the way to the module, to the pack, we lose a lot of energy during the process. Okay, so that also means that we have a lot of room for improvement. So actually, this is the first time I'm talking to the public that this year is 200 years celebration of the element lithium being discovered in 1818. So you probably think that, oh, this is a pretty old field, right? 200 years, surely what are you doing in this field? Lithium-ion battery is first commercialized in 1992, only 26 years. Right, so I'll give you a little bit of history of the battery field later. So when we talk about batteries, I think one of the problems you often see in the news is that somebody flashed the big news saying, yes, we can do fast charging. We can charge something within 5 minutes. Because people are very impatient. When they drive electric cars, they do not want to wait for the 30 minutes charging. They want 5 minutes. So I think it's a good opportunity for me as a professor to basically, argue about the difference between power and energy. It's important, okay? So what's power? Power is what? Okay, so you look at all your appliances. Your light bulb is a few watt. Your hair blower or the toaster is a kilowatt, okay? And the world has a terawatt problem. Yes, that's true. But what is watt hour? That's the energy unit. Please do not mix up between the units between power and energy. In fact, I have a lot of chance to talk to the reporters, and oftentimes, half of the time, I'm trying to stress the difference between power and energy. Here, if you have the light bulb lighting for 16 hours, the amount of energy is the same as you operate your toaster for 1 minute. Your toaster is 1,000 times more powerful, but it only operates for 1 minute, right? So the power of these two devices is 3 magnitude order different. They are not the same at the power level, but the energy, delivered energy is the same, or the required energy amount is the same. Why is it important? Because we look at a lot of the application for the batteries, right? People want to use it on the wearables or credit card or laptop, Tesla car. All right, so now look at this number. Okay, so first of all, watt hour can be translated to joule. Okay, 1 watt hour is actually a very big number. That is 3,600 joule. Watt hour is a big energy number. So you can check when you replace your cell phone how much energy is in your cell phone. It's tens of kilojoules of energy in your cell phone batteries. Now, if you have a 60 kilowatt hour batteries in the Tesla car, okay? You want something to be charged for 1 hour, 65 kilowatt hour batteries, 1 hour charging, your cable can handle 65 kilowatt. Okay, I can guarantee none of your household have this kind of power. Make sense? I don't think any of your electric outlet will give 65 kilowatt. Right? Okay. Now, Tesla built a lot of supercharging stations. Good for them. We need more of those, but they usually do half an hour charging. That means the cable is special. They actually use special equipment that can enable you to draw, say, 100 kilowatt power from the grid, right? It is a very, very challenging, engineer-wise, it's very challenging. Now, somebody told me that they want to do it in 5 minutes. That is, can you imagine what kind of cable we need to build for 5 minutes? Basically, you need something of megawatt. You need basically a dedicated power plant for fast charging your car, right? So I think when the public, this is where I feel it's important for me to come and talk to the audience. I think when the requirement for the fast charging for the cell phone and for your iWatch, we can make that happen. But for the electric cars, I think 30 minutes is probably some of the limit that we will reach, okay? And then, of course, when we talk about grid storage, we're doing even bigger batteries. So in the Tesla car, one car consists of over 6,000 batteries. In those containers, they have tens of thousands of single cells that put together to try to store electrons from solar and wind. So we have 5 of them in UC San Diego. We actually have our own microgrid and our own battery storage. Right? So just to put your skill bar correct, our brain is around the same power consumption as the computers. Literally, if you put a light bulb there, you probably will light up the light bulb. Okay? That's why I always encourage my students to work more, because you actually, consume a lot of energy by thinking hard, okay? Okay, so what's the roadmap? So I'm going to go through this real quickly because it's a little bit too technical, but just to let you know that these are the commercialized technology, and we, the scientists, all these colors are the new chemistry, new materials. We have something on the horizon, ready, right? Of course, we have a lot of problems to solve. So I'll give you a couple examples of what are the challenges we're going to face. But I can guarantee in the next decade, you will see that the doubling or tripling the energy density of today's battery technology. And what does it take to do that? And there is a global race who reached there first. As many of you probably not aware of, that a lot of the original battery materials are actually invented by scientists in Europe and the United States. And right now, of course, majority of the manufacturings are being done in Japan, Korea, and China. I think over the last few years, China is really, really building a lot of the manufacturing capacities. So, this is also a potential topic we should probably discuss, that, how we can maximize the early stage research that really happened in this country, that to kind of benefit more of what we have been doing here. So in terms of grid storage, I think the most important thing I want to stress here is that I think a lot of you are aware of pumped hydro. Pumped hydro is a very cheap energy storage source, but for geography limitation, we can't build pumped hydro everywhere. So battery is still, it's true, it's still 10 times more expensive than the pumped hydro, okay? But in the grid, people have to think about a power cost, which is typically not in your electricity bill. So I'm sure for this audience, so when I teach in the class, I ask students, how many of you pay electricity bill? Actually, nobody raised their hands. But I think all of you here pay electricity bill, right? In the bill, you don't get the dollar per kilowatt number. You only get the dollar per kilowatt hour. That's how they charge you. But to have a functional grid, you actually have to have the dollar per kilowatt. You have to pay for the performances because all our appliances work on 60 hertz. You have to make sure that the voltage and the power meet with the requirement. Right. So actually, the batteries are very low cost for the power because batteries typically very good at fast response, but hydros are not. Okay? So I think scientists are working really, really hard to make that happen. That our goal in the next decade is to increase the energy density 2 to 3 times and lower the cost 2 to 3 times. But, there are a couple of things happen in the last couple of decades, I think enable the scientists to do things a little bit differently. One thing is what we call the materials genome. So basically use computation method to help the humans to plan for experiments. We do a lot of database, you heard the buzzword about big data. We can actually do big data, machine learning, for what's already happened, and then we design new materials process to accelerate this pace. So typically materials discovered from the lab to the market takes about 2 decades on average, 15 to 20 years. And I think for a lot of the energy materials, we cannot wait that long. So we will have to implement some new tools to make the things, the discovery to lab happen a little bit quicker. And the second thing, so basically it's an X-ray machine that shine on the batteries. When battery is being operated, those dots, they will move around. Okay? When they move, that means the materials, like I told you, it's breathing, it's changing. And the process is actually reversible. When you do many cycles, you see them keep moving. All those tools, they're not available 20 years ago. And today, they're readily available for the scientists who are working on the batteries. So I think some of the audience here probably experienced the 70s energy crisis. You probably already know more than me what this country has put in to enable renewables or batteries. I think I don't dispute the fact that a lot of brilliant minds have already worked on this problem, but I think there's something fundamentally changed in the last 2 decades. One of the most important thing is this commoditization of the lithium batteries. So 2005 is the year when I became a postdoc. I'm basically finished my Ph.D. and building my career at that time. The battery is around $2,000 per kilowatt hour. Okay? Today, I have a line drawn here in 2015. The scientists using what I have told you, all these modern tools, we were able to deliver, improve the battery. So this is a normalized graph, right? So dollar per kilowatt hour, so dollar per energy. So the more energy density you improve, the lower the number will become, right? And then, of course, the lower the cost, the number will reduce. So what has fundamentally changed? When I was a graduate student, or in 1992, when it's commercialized, majority of the materials used in the battery, lithium-ion batteries, is lithium cobalt oxide. Cobalt is a transition metal that I was talking about. Now, my PhD topic is to look for replacement of cobalt, because cobalt is mostly concentrated in countries like Congo. I think you've read some articles lately in New York Times about the child labor in the cobalt mining. The other thing is cobalt is also, the isotopes of the cobalt is for weapon development. So a lot of the scientists actually work very hard to replace cobalt with other elements, more earth abundant, like iron, nickel, and manganese. And the other very important thing that has happened is that the manufacturing, the scale is really happening in the 2000. So we meet the expectation, this paper was published in 2014 saying, oh, maybe we will reach $150 per kilowatt hour. I think we're really, really close. Right now, I think we're like $200 per kilowatt hour, 10 times less in its cost in the last decade. Right, so this is very, very encouraging news, but I want to take this opportunity. I have a few minutes left. I just want to kind of do a very quick test to see if you guys know the history of the battery research. All right, first picture, Benjamin Franklin. Okay, in the 1760s, he's the first person who coined the word battery. Second person, Sir Alexander Volta, okay, the Volta Power, 1800s, right? The third person, probably a lot of people do not know him, Pascal. He's the inventor for the lead acid battery in the 1860s. The fourth person is the inventor for the nickel metal hydride batteries, Sanford Olszewski. All right, now all of them, the pioneers, have passed. Okay, so in the 2006, when I go on the job market, I said I want to work on batteries, and then actually quite a few very famous senior professors said, oh, I don't understand why you want to work in this field, it's really old, right? So I hope, obviously they are not right. Actually, in the field of lithium-ion batteries, these two gentlemen, Professor Stan Whittingham, 1976, first science paper about lithium batteries. He used a lithium metal together with titanium disulfide, not oxide, but sulfide. He built 2-volt batteries. And that's the first publication on lithium batteries. Now, in the 1980s, Professor Goodenough, John Goodenough, yeah, his name is Goodenough. Actually, he was the one who first time discovered the lithium cobalt oxide. So lithium cobalt oxide is not a natural existing materials. It's a synthetic materials made in his lab, right? And both these gentlemen, their batteries last very, very long. That's how they look today. And they're still very active in the battery field. So I always joke that, maybe they last longer than some of the batteries they have made. So we have to do better for the batteries. Batteries should be able to last 3 decades. I mean, that's our goal in the future. We will make batteries last for 1,500 cycles, let's say, right? So, and by the way, these two gentlemen both are my advisors and mentors, and I think we're standing on the shoulders of these giants when we move forward, and it's very important that, I think their contribution to the field are properly recognized. So I have a lot of students do startups. So this is another potential ethical issues that people might ask me, because in those engineering field, plenty of opportunities, plenty of, people want to give money, and then they want to see how, this technology can be profitable in the future. So me as a professor, my products are my students, but my students are free to do the startups. Okay, so when they do startups, I always give them those 3 advice. Number 1, battery startups are very high risk, capital intensive endeavors that require scientific creativity and engineering breakthroughs. They really have to remember that this is a true teamwork to make something like this work. The second advice I always give is that, think about the competitions from global, all the big companies, LG Chem, Samsung, Panasonic. CATL is the uprising Chinese company that they will be, together with BYD, they will probably be one of the majority market share for the batteries. Now, the last one is when we do the batteries, we have 3 different fields, wearables, for e-mobilities, for transportation, or the massive energy storage for renewable. And they all have very, very different requirements. Okay? So I'm coming to the end of my talk. I think I mentioned that we have a lot of potential things on our roadmap that scientists are working on that we hope that will solve some of your questions. Okay? I think one thing people are very concerned is the safety for the batteries. Right? Of course, we are trying to raise the energy density even more. And then I hope we will have some discussion about other chemistry, why it has to be lithium. Why can't you have sodium batteries? Think about it. Sodium is more abundant. Why can't we make batteries based on sodium chemistry? We can. Actually, in the 1960s and the 70s, lots of engineers and scientists worked on the sodium batteries. Right? There's a lot of reasons why sodium did not succeed. I think lithium is the most electropositive ions So for sodium, the battery voltage is a little bit lower. So ask a lot of the people who work on the earlier electronic industry, they really want something work around the 4 volt. Maybe not true today. I think a lot of the transistors and the electronics work on the low power, but at that time in the 90s, a lot of them need a 4 volt, single cell 4 volt, or dual cell, still build up the voltage for more than 4 volt. And then, of course, I'm from Nano engineering department, so Nano is always very important for us to improve the battery performance. So at UCSD, I'm not the only person who work on batteries. We have a team of researchers work on all those different aspects of energy storage and the conversion. We actually have this tagline said we work from atom to microgrid. Actually, UC San Diego does have a world-renowned microgrid. We supply 80% of our own electricity. We have professors work on many different aspects of energy storage, and this is a wonderful platform. We're slowly gaining the reputation about, they can ask us for advice and suggestions if people or companies need help. Now, let me finish by this slide, which is a little bit old. It's old data, but still staying true. So when you buy electricity, you get something from a day ahead market, DAM, and then real-time market. So electricity market looks like the stock market, no? Okay, if you buy a day ahead, it's very stable. Yeah, you on the 15 minutes real market, look how much it fluctuates. Right? So this is where I think in terms of modernize our grid and how you can still do sustainability and you are green and still make money. I think about it. If you have a battery, you can predict at any time the need of the electricity demand or sucking any electrons when you need. There's plenty of possibilities there, right? So Morgan Stanley did an evaluation last year, just call our batteries the underappreciated disruptor. So I think hopefully I have shown you some of the things that we have been working very hard on to make better batteries. And I'm very fortunate that in the last 10 years, I have been receiving the support from both the federal government and the private industry. And I pay a lot of attention to involve girls in the energy research. And you see close to half of my group members are ladies. And I think it's very, very important. And a lot of the female scientists and engineers love to work in engineering, the energy-related field, because we feel this is the field that closely related to the future of humanity, and we really, really want to make a contribution. So with that, thank you very much for your attention.
So I see we already do have one question, but I wanted to do sort of an overview piece first before we start that. And actually, it was a perfect segue for the end of your talk. So I noticed when you talked about the people who have built up the history of batteries and understanding electricity and leading us to where we are, unless I'm mistaken, every one of those people was a white male. And there are a number of programs in place right now that involve women in science. And there's also San Diego Festival of Science and Engineering, which is going on this week. This program is featured in that, and you're featured in both of those for that reason. I wonder if you could give us some thought about how much engineering as a whole, or at least your field of engineering, has changed. Your group clearly has a lot of women involved with it. So where is that going? And
yeah, I think we're definitely making progress. I remain very optimistic, and I think I have a lot of good white male colleagues that actually they are very supportive of the promoting and encouraging female to get involved in engineering and the science. I think most of the obstacles we have faced in the past, I think some of them have been addressed. For instance, if you look at a lot of the engineering classes today, we have close to 40% female students, for example, in material science and engineering. I think in bio, you have close to half of the populations. Right now, a lot of us are actually working on the retention and the promotion of the females. And we're definitely, I'm not saying there is no challenges, but I do think that at least this is the reason I come to the United States. I'm not sure I'm allowed to say that, but I think in Asia, we are actually still quite behind, and the US is actually, I mean, perhaps compared to Europe, we're still having more work to do. I mean, countries like Norway and, you know, they have more females involved in the science and engineering. But I actually think that this is one of the big attraction for me to be in the US. I do believe that at least the people acknowledge there is a problem and how we can address the problem. So I'm happy to say that at least in UC San Diego, the current administration is doing a lot, trying to encourage more female students to be involved in the STEM field.
Yeah, and what you just described is my observation too, that in many fields, in engineering included, you do see a higher percentage of women in those classes, which means we are now taking advantage of the full population instead of only half. However, the pipeline seems to still be very leaky in terms of getting into faculty positions and being promoted. And so it sounds like that's an area you're working on.
Yes, yeah. I think a while ago we just resolved the equal pay problem on the campus. I actually was quite shocked to find out I'm 15% less paid by, yeah, it does happen, but I think most of the time it comes from the fact that, you know, I learned to be a better negotiator now. But when I first started the job, nobody taught me I should negotiate, right? And then the other thing I found very interesting is that if I make noises, and a lot of people think I'm troublemakers, but my male colleagues, they can make a lot of troubles, and nobody call them troublemakers. So actually, I now treat the word troublemaker as a positive label. It's fine to be the troublemaker.
Very nicely done. Good. Thank you. So, we have some questions. Yeah.
I have some questions about safety, and I know that batteries are made safe. You can buy one and put it in your car. You know, it's nice and safe. But I'm wondering what happens with these electric cars if one gets into an accident on the road. And this came home to me the other day when I test drove a Tesla S. And that is the hottest hot rod I ever drove. I mean, that thing goes like crazy. And I actually, after a while, I was afraid of it, you know. And I don't know whether there have been accidents or not. You know, but what could happen? And for example, can you get electrocuted? Can something happen to the battery that, you know, it would break and electrocute the passengers? I had two other experiences just talking about safety. One was with my garage mechanic, who, you know, I asked him, "Are you servicing electric cars yet?" Because we were thinking of getting one. And he says, "No, we can't find anyone to work on it because they're afraid if they do something wrong, they're going to get fried." You know, that was one thing that happened. And the other thing happened to me personally, that normally I wear hearing aids. Well, I shouldn't say normally. I generally neglect to wear them, you know, but periodically I put the same hearing aid on. And I noticed it wasn't working as well, so I had it checked. And they took out the lithium battery, and it was almost double the size. And I began to wonder whether this thing could have blown up in my ear. So
it's a good question. So it sounds like there's, you know, questions that may or may not be worries of fire, explosion, electrocution. Yes. So what do we have to worry about?
I'm pretty sure electrocution is not a major worry. Most of the car batteries, maximum voltage is, you know, a few hundred volts, and then it definitely won't, you know, I think unless you really purposely put your hands on the positive and negative electrodes. Usually it's not high voltage enough to create the arc to electrify anyone. About the gassing, so the reason it expands by double is actually due to a gassing problem in the electrolyte. And I didn't have time today, but a lot of the research today is to replacing the flammable liquid electrolyte with the solid. We are well aware of the safety problems. So for your hearing aid, I'm not doing advertisement, but I know some companies actually use the battery based on zinc silver oxide chemistry. You can check them out. Z-Power, they actually supply batteries to some hearing aids. That is a safer chemistry for less of those because it's based on the aqueous chemistry and the water. So lithium-ion batteries I didn't talk about today is based on non-aqueous. So everything used in your batteries has no water in it because water cannot sustain 3 volt or 4 volt. So everything in your batteries is water-free, and it's actually built on organic molecules that are extremely flammable and can decompose and generate gas. So your safety concern is definitely real, and for this reason, many auto companies actually only keep the electric portion as a small portion right now. It's not their major. Tesla is the only company, they are the outlier, right? They came in and they do all electric. The other companies, they have their other car business while they are actively working on the electric car. I think the safety issues that you are mentioning, it's being worked on by, I guess, almost every single auto companies. BMW, Daimler, Toyota, everybody knows the safety concerns. So I think I don't have the answer for you right now, but your concern is valid, and we hear your voice, and hopefully one day we will demonstrate to you that when the car gets hit, the batteries can fail safe. So actually in the I guess defense-related research, such batteries has been built. So as you know, a lot of the research that are related to the defense area, they don't care about the cost. We can actually put down safety measures and make batteries extremely safe, so safe that if you hit the bullet through, it will not explode. It's possible, but it's very, very costly today. So I think the solution can be figured out, but we cannot do it without the cost reduction for a lot of the technologies.
This is a good reminder of something I heard years ago when I was a computer programmer for the first time, and that is that you would tell customers that they can have things good, fast, or cheap. They could choose any 2 of those 3. You can't have all 3. And your list actually is safety, energy, cost, and power. And you might like to have all of those, but you're not going to have it really cheap and have it very safe and provide plenty of energy and power.
Yeah, I think it's a very good observation, because many reporters that when they ask me, I always suggest them to do the spider chart when they compare technology. So the axis you mentioned, energy, power, cost, safety, and we also need to include the recyclability, environmental friendliness, and also the cycle life. So when we evaluate any technology, we need the spider chart to see how much area the new technology cover, instead of only, typically people only look at the 2 axes when they compare the technology, 2 or 3.
And it's just unfortunately not an option to get everything all at once.
Yeah, for company maybe not, but scientists are always allowed to dream, right? So we dream about. Yes.
Good. Thanks. Ray, so.
Yeah, earlier in your talk you mentioned about how people are impatient and they want to charge things very quickly, and you set the limit on how large a cable to conduct, so many amps and try to charge, say, an automobile in just a few minutes. Independent of the size of the cable, is there a limit of the batteries themselves that you can only jam so much electric charge in there before it overheats, expands, or fails in some other way? Or maybe just lose lifetime?
Very good question. Yeah, so the battery materials, the layered oxide I talked about, they have diffusion limitations. So in fact, if you do, some materials can kind of suck in all the lithium in 5 minutes, some cannot. And especially graphite, the carbon things, at low temperature, cold weather like Boston, really do poorly. So actually, if you make an observation of other accidents occurred with the Dreamliners, that when they changed to lithium batteries, almost every case happened in cold weather in Japan, Boston. Actually, I think we know the problem really is because when you do, so cold charging is similar as when you do room temperature fast charging. You're trying to shuffle lithium ion into something where the materials actually has no capabilities of taking them. So the danger on the negative electrode side, which is the carbon or graphite today, is very, very problematic, because if you plate lithium metal, instead of it's in the ion form. So remember our battery, the proper name is called lithium ion batteries. There is no metallic lithium involved in the batteries. So when you plate metallic lithium, you can potentially grow something called dendrite. So if the metal does not grow flat, it goes kind of like trees. Yeah, that shorts your batteries and cause a lot of safety problems. So I think fast charging is quite problematic for cold weather. So I think in California, you don't have to worry too much. We rarely get to freezing temperature. But in the cold weather, I think it has to be really, really well managed for the fast charging. And then if the users of Tesla could help it, I suggest not to use fast charging too often. It does affect the battery life adversely. Yeah.
Good. No, thank you.
With going to other planets or to farther reaches of space, what challenges do we face with batteries degrading, and how can we prevent stuff like this, like a space station just dying all of a sudden? How can we prevent this? And then, do you consider nuclear energy to be some sort of clean energy, and how do we store such massive amounts of energy, and how can we use this knowledge we have of storing massive amounts of energy to our benefit for other things like my phone or computers, for example, stuff like that?
Okay, thank you for the very thoughtful question. For your first question, for the space exploration, so I think NASA, they actually have a lot of programs where the batteries research is involved. So one of the big challenges for space application is actually low temperature performance. Because the temperature out of space sometimes can get really cold. And then
colder than Boston.
Yeah, so if you Google something called liquefied gas electrolyte, it was a science paper published last year from our group. We're very proud to say we created a world record for minus 60 degrees Celsius battery operations. So we're working actually together with NASA to kind of see, we have a program from the NASA to do those kind of low temperature, extreme temperature batteries. And on the other hand, the reliability for the space application is very important. So typically they do not try anything that is not reliable. So I think a lot of the primary batteries, batteries that being used just once, non-rechargeable, they have higher reliability. When you need to use them, they actually work well. So I think they use primary batteries a lot. Of course, now we cannot create a space junk as well, right? So we have to get the battery back, and hopefully I think you will see more and more rechargeable lithium batteries being used in the space application. In terms of reliability for lithium-ion batteries, most of the manufacturing is done by robotics today. The failure rate for the lithium-ion batteries in today's top manufacturer is 1 in 10 million. Yeah, so in world circulation, we have a few billion batteries, so you only hear accidents here and now, and the statistics really matches with the manufacturer's numbers. We are improving a lot on the reliabilities of the batteries, but still we have not solved. If you do have a failure, it kind of catch fire and explode. It does not fail like your alkaline battery is very, just some electrolyte leakage and no major damage. For your second question, at least in our center, we do not consider nuclear energy as a clean option, just because at the moment the nuclear waste is still something we cannot handle. So I didn't have a chance to talk about the lithium battery recycling. We're making a lot of progress on recycling the lithium-ion batteries and regenerate it. For nuclear, I think as long as the waste problem is not resolved, we cannot actually consider this as a complete clean energy. And also our experience with the Center Offray here, as you know, when the nuclear power, some part of it is broken, the entire facility has to be taken down. Unlike some of the battery facility we have, if we spot one batteries has trouble, we just replace that one, or we replace that module. Things can be partially shut down. So the whole running and the maintenance of the nuclear is really something I would say we have not figured out. So at UCSD, we have another group of faculties who are working on that, but currently is not included in the Sustainable Power and Energy Center at the moment.
Thanks.
It seems to me that there's two areas in our society now where batteries are the key issue, determining the economic and physical feasibility. That's one, being able to cut yourself off from the grid and use home solar so you don't have to have the whole infrastructure. And the other one, of course, is cars. And they're big batteries, bigger than what we've had before. They have a lot of the issues that you talked about, but it would seem to me that those are really sort of more urgent, and I hate to say more important than like massive scale batteries for power plants. That, you still have the same distribution problems if you have a battery, so the battery doesn't really make a huge difference, whereas in cars and in the home it would make a transforming difference.
Yes, thank you very much for the comment and the question. In fact, this is what I'm trying to talk to Washington about, the importance of distributed energy storage and usage and instead of centralized. However, as you know, that majority of the electrons are monopolized by utility companies. In fact, we all of us in San Diego as a customer of SDG&E, we don't have a choice, right? We cannot choose. And then I always, as I told you that the scientists like to dream, I always want to dream that they will sell my electrons, how much for the green electrons from the wind, how much blue electrons that come from the solar, and how much is the red. But at the moment, all those cannot be done because the grid is, at the moment, we don't have the control. Basically, they are being controlled by the utility company. So what you said is a lot of the scientists or engineers would like to happen is for some organizations or government or companies or together to look at the option for distributed energy generation and storage. And this is the whole reason why I initiated the Sustainable Power and Energy Center. I think from the academic point of view, we have a lot of students who are eager to work on those problems and then who are searching for opportunities to implement. I think in San Diego area in the last few years, we did have a few positive experience with some companies, but it kind of never grew bigger. And I would love to have an opportunity to discuss why we couldn't convince the utility companies or the government to make big changes. And this is the topics that I would love to have more in-depth discussions.
Given the importance, as the question suggested, of energy to everything we do, the question that this audience might ask for themselves, and you might help them think about, is what can they do about trying to think more deeply about our energy production and energy storage to change the model to one that will ensure, for example, more distributed sources of energy. What can we as voting citizens do?
I think it's a very difficult question to answer because at the moment, I think a lot of our research kind of stopped because of the lack of fundings. I think this is where, this dilemma of, so when we work with industry, we really want the industry to support supporting our students. The money does not come to the professors, it goes to education and supporting the students, right? So I think regardless what we get the federal support or not, I mean, it is an important task that a lot of us are trying to speak with philanthropists and people who, it's good to do cancer research and prolong lifetime, but I do think that if we do not have the good balance between cheap, abundant energy and water versus the increase in population and the longer lifetime, the world will run into a problem. And this is where, I think the topic is so important. I am, because I come from Singapore, I actually, our government, they are very strict. Somebody said they're very strict, everything is ordered. But here I do see a vast difference in the style of how things are being governed. But US does have this fantastic culture I've never seen any other culture, is that there's a lot of philanthropists that were willing to support a good cause. And this is the very, very important thing. I think if we want to make differences, I'm hoping there are individuals like that stand up saying that I'm going to do something different.
Yeah, so when we were talking about this talk at first, there was questions for both of us about where the ethical issues are, and you've just highlighted a very large sort of all-encompassing ethical issue of the trade-offs we make between deciding whether we want to pursue healthcare, better healthcare, we want to pursue sources of water, we want to pursue sources of energy. Yeah. We ideally want all of them, but again, you can't have everything. So how do we make those choices?
I think the important number people should look into is that for the philanthropist money, more than 90% is for health right now.
So maybe that balance should change. This is a wonderful presentation.